All right, so the next circuit that is in line with the filters, the rectifiers is the filter. So remember that we are talking about the application of DC power supplies. We are converting from AC to DC. So the purpose of the filter is, so when a signal, whether it's a half wave or a full wave, when it passes through a filter, which is used to remove any fluctuations in the output voltage in order to produce a, remember we're looking for a constant level of DC voltage. It's used to smooth. So in here the example shown, it's a full wave rectifier. So for example, the signal of full wave looks something like this. So when this signal passes through the filter, then the outcome of the filter looks like something like that, where here the fluctuations are very high. So that fluctuations, if you observe the peak to peak, the fluctuations for peak to peak were greatly reduced, right? So that's the purpose of filters, is to remove those fluctuations so that we will effectively get as much as possible. Again, filters cannot do perfectly this job of providing a fixed level of DC voltage, but to an extent they can remove these ripples. Not 100%, but there is always going to be some ripples present even you have a good filter. But the signal after the rectifier, whether it's a full wave or half wave, it has to passes through the filter. So there are three formulas that we will be using. The last three formulas on the first page of your formula sheet, meaning the right below the table 2, right? You're talking about ripple value. So these fluctuations has a term that we use called as ripple or ripple factor. This is usually expressed in the percentages. So for example, 1% ripple factor, 0.01% ripple factor. A perfect power supply should have no ripple factor. Of course, that cannot be done. So you always see power supplies. Usually when we purchase a power supply, we will know that what ripple percentage is. So usually they will be somewhere something like that, like 0.03%, 0.05. So extremely small, but definitely it's not going to be zero, meaning that you're never going to get a perfect straight line. Visually, you may not see it, but the ripple is always going to be exist in your DC signal, whatever that DC power supply is. So there are two things involved once the signal passes through the filter. If you look at those two formulas, what you will see is VR peak to peak. That's called as a ripple peak to peak. And another value you will see is VDC, which is the DC voltage. Correct? And if you take the ratio of these two, then you will get a ripple factor, which is when you need a percentage, you multiply it by 100. Right? It's pretty much the importance given to these two because the ripple factor is just the ratio of it. So what is this VR peak to peak and what is this VDC? Remember that in our application, we are trying to see how much DC voltage are we getting, correct? So this formula is able to tell us exactly how much DC voltage are we looking at. So let's take a look at first what this filter is, what is going to be inside this filter, and then we will see how to use these formulas. So a filter is nothing more than a simply adding a capacitor. So That's pretty much acting as a filter. So in this example, what type of rectifier is this? Half wave. There is only one diode, correct? Remember, usually when we're dealing with circuit with a half wave, this is how our circuit is, correct? Correct. We always see resistor. We always see resistor immediately after the diode, which is our load for that matter. But now, when you add a filter, you see that after the diode, a capacitor is placed, and then the resistor. But how these two are connected? So how those two are connected? How the capacitor is connected to the resistor? Is it connected series or parallel? So it is connected in parallel because it's sharing both ends, correct? What is going to be the same in parallel? The voltage is going to be same in the parallel, meaning that whatever the voltage on the capacitor is, the same voltage will be available on the resistor since they are placed in parallel. So this is basically our source, this is the rectifier, this is the filter, that's our load, right? So a filter is nothing more than a capacitor. Usually power supplies uses a very big capacitor. The higher the capacitor you go, the better filtering action would be. The better filtering action means the lower the ripple would be. Remember, we are aiming for 0% ripple, right? So we could use very big capacitor to limit the ripple. All right, so this is how the circuit operates. Again, the same concept applies to full wave rectifier as well, but in a slightly different fashion. So again, remember that in parallel, the voltages are going to be the same. So this is what will happen. So initially, when the signal on the positive half cycle, remember the capacitor is placed after the diode. So meaning that the signal voltage has to overcome the 0.7, correct? So let's say, for example, you are at 5 volts peak on the input signal. So as the input signal is increasing, as long as it crosses 0.7, the diode will become forward bias, isn't it? Which is like a half wave rectifier. But once the diode allows the current, then that voltage is used to charge the capacitor. Right? Is that true? So capacitor is, so whenever you have a current flow allowed by the diode, then that voltage will be used to charge the capacitor. So that's why as the capacitor charging, the maximum value it can charge is to whatever the input voltage minus remaining voltage, which is nothing but this is the same formula that you use for half wave rectifier. V peak input minus 0.7, correct? So during the first quarter half cycle, so this is what will happen. During the first quarter half cycle, as the input signal is increasing, the diode becomes forward bias as long as you cross that 0.7 volts. And then the capacitor starts charging to a maximum value of 4.3 in this case, correct? Since that capacitor is placed in parallel to the resistor, the voltage on the resistor would be also exactly the identical, which is following the same shape. But what happens after that is what would be different. So again, I'm going to state a couple of things on what we want, but what actually happens depending upon the rectifier. So let's say that capacitor is already holding that 4.3. Remember that what we are looking at is, we are looking at something like a straight line, correct? Right? Because in our application, we are looking for a DC voltage, correct? But this is what will happen. When the capacitor charges initially, let's say it is holding that 4.3 volts, which is somewhere right here. Then immediately the signal voltage will start going down, correct? The capacitor plate right here is already held at 4.3 volts. Because remember, capacitor acts as a temporary battery which stores that 4.3 volts until it discharges, correct? There is only one way it can discharge, through the resistor. But when it is going to discharge, when the diode becomes reverse bias. So for example, when this diode becomes reverse bias, then it's not going to charge anymore. The only thing the capacitor can do is to discharge. But the question is, how much amount of voltage do we want it to discharge if we want to maintain that 4.3 volts like that? How much amount of voltage we want capacitor to lose if we are looking at this signal type? So we don't want to lose any of the signal, is it correct? So that's what I'm saying. Ideally, this is what we are expecting, correct? We don't want, so once the capacitor charges to 4.3 volts, we want to hold that charge so that we can get a perfect straight line, correct? But practically, remember this guy right here? What is that? Tau, correct? R times C, which is the time constant, which will tell us how quickly the capacitor charges and discharges. So now we're going to have some value of resistance right here and some value of capacitance, of course. So this charge am I expecting to keep is not going to happen, but what will happen is, once the capacitor charges to that 4.3, when the input signal is start going down, the diode will reverse biases, but the capacitor will start to discharge towards the load resistance until the diode becomes forward bias again, which will not happen until the next positive half cycle for a half wave rectifier. Is that correct? So let me put that in a different perspective. So let me end this one. Let's talk about, wow, I hope it doesn't crash. All right. So this is our input signal right here. This is our source. This is what we are feeding in. Once it passes through the diode, so let me draw a couple of cycles. Once it passes through one diode, this is what will happen, correct? Right? Because it's a half wave rectifier. Once it passes through the capacitor, this is what will happen. Again, forget about the voltage levels for now. So initially the capacitor starts charges to the maximum value, minus 0.7. After that, from this point, the diode will be forward biases. But from that point onwards, the diode starts reverse biasing for the entire. So what will happen is, this voltage has to discharge through the resistor. Depending upon how fast the capacitor can discharge. Again, we don't want it to discharge, correct? Because we want that line to be held as fixed as possible, meaning that you need to have this time constant very high. That means it takes a lot of time for it to discharge. So either you use very big capacitor, that's usually purpose, as I mentioned before, you use a very big capacitor to just do that. And once it hits the next positive half cycle, then it's going to charge again, and then it will effectively discharges. So yeah, there is no specific name for it, but you can call it a speed breaker if you want. But I don't have answers to some of your questions. All right, so you see this peak to peak right here. This is called as the ripple. We want that ripple to be how much? Ideally, how much ripple we want that to be? We want 0. We don't want any ripples. We want the signal to be. So once we keep that charge, we want to hold it. So we want that ripple to be 0. This ripple has a formula. You can look at on your formula sheet. It's called as VR peak to peak. Right? And there is another formula too right below, which is called as VDC, which is this voltage right here. So that's the behavior if you add a capacitor to the circuit. So can you think about a minute on, because of this reason, which rectifier you prefer? Half wave or a full wave rectifier, and why? We just talked about this explanation. So if you're thinking about this explanation, which rectifier you prefer? Again, we want to hold the charge as long as possible. Because if you use a full wave, that's 2 peaks coming one next to each other, which will not allow the capacitor to discharge or lose that much of amount of voltage. That's one of the reasons why full wave rectifier is heavily preferred if you want lower ripples. And that's why in most of the applications, always full wave rectifiers is used, because its frequency is double. Because you are getting those peaks. Here, the distance between the peaks is, they're farther away. Correct? That means the only thing capacitor can do is discharge. But if you have the shorter time between the peaks, you are lowering the discharging value, isn't it? Then you will get less ripples. So that's why full wave rectifier is preferred, because it has a twice frequency as opposed to a half wave. It's discharging to the resistor. The resistor is being added.
So the second graph says what?
Which you're talking about, this one?
So the one on top of that one in the middle.
So this is your half wave rectifier. That's the signal coming off of the diode itself. This is the signal coming off of the capacitor. Yeah, remember that it's a half wave rectifier. It's only one diode we are using. So does that make sense? Like last class we talked about is just with the diode. So because diode, when it passes through the diode take away half of it, correct? Which will be this. And when you don't have a capacitor, this is it. You're done. But if you have a capacitor, then you're going to have something like this. Yeah. After the diode, you have a capacitor. So that's pretty much what happens if you have a capacitor. Again, this same concept is true. So during the remaining portion of the cycle, the capacitor should discharge through the load resistor depending upon RC time constant. Again, usually you require a very big capacitor. Today in the lab, you will see this too. Having a smaller capacitor versus a bigger capacitor. What you are expecting is what you will get out of it if you have a bigger cap. And what's the benefit of having a bigger cap? So your ripples will be smaller if you have bigger capacitor or bigger resistor, but usually we don't have a control over the load. So the design goes with bigger capacitor. So in today's lab, you would be using, I think, 1 microfarad versus 100 microfarad. So you will see that with 100 microfarad, you barely see the ripples. But if you put like 1000 microfarad, visually you can see it. Ripples will be still there. But it's like in millivolts or even microvolts. So that's how the signal looks like. The larger time constant, the less capacitor with discharges. So that's pretty much what a filter is. It's nothing more than just a piece of capacitor in there. All right. So it charges in the forward bias. It discharges when the diode becomes a reverse bias. And the amount of ripples. So its charging path is towards this direction, but the discharging path is towards the, of course, the discharging path doesn't include the diode, so it's going to be just those two. So it's going to be towards the load. And then you forward biases as soon as the voltage exceeds it, the capacitor now charges. Same thing will repeat, it discharges and so on. So this is the circuits on the multisim. So which one you think will have smaller ripples? Which one you think in here will have smaller ripples? Because of?
Because your resistance is larger, R times C.
So here it's being chosen same capacitor, but you can see here the resistor was increased. So no matter which one you increase on the time constant, you will have a larger time constant. And you will see the difference right here. You see the ripple right here is maybe that much compared to the ripple right here. Right. But this technique is not that used like increasing the resistor value. As I said, resistor is considered as a load, which the designers don't have control over. So it's largely the capacitor. Either or, yes. So according to the formula, it's either or. Either you can raise the resistor or raise the cap. But the actual design goes is raising the capacitor, not the resistor. Again, the smaller the ripple is, the better the filtering action would be, which can happen with a larger value of capacitor. So that being said, which one should I use, half wave versus a full wave? So because the output frequency of full wave is what? Twice, as you can observe in this multi-sim circuit, I have 2 kilohertz frequency. Here the frequency becomes 4 kilohertz. But what type of rectifier is this? Full wave of what kind? There are two full waves we talk about. This is a bridge, but still full wave. As you can see, the frequency was twice. That's an advantage is because full wave rectifiers are easy to filter because the shorter time between the peaks. And full wave rectifier will always going to have smaller ripples for the same amount of capacitor or resistor when compared to the half wave.
Where's your, I don't see a capacitor in
I don't have a capacitor in there. It's just a rectifier just to show the frequency one. In tomorrow lab, you will build this with the capacitor, without the capacitor to see what their filtering actions would be. Pretty much. Today you will see with capacitor, again without capacitor for half wave. Next lab you will do full wave. All right, so now it comes the fun part of how do I use these formulas. Some of these are pretty straightforward and some of these are you need to know how to use your calculator. Right? So, but always remember that does the filter comes after the rectifier or before the rectifier? The filter comes so where is the capacitor, before the diode or after the diode? So the filter stage will come after the rectifier stage. Remember the power supply block diagram? First thing is you're going to have a transformer, correct? And then what it will be? After transformer, this is where you will have your rectifier. After the rectifier, it is going to be the filter and then regulator and so on. But most importantly, the filter stage comes after the rectifier. This is very important because you can see these formulas. Couple of things are very important. This voltage that you are multiplying, what do you think that voltage is? So what do you think this voltage will be in our calculations? That's exactly right. So these voltages are nothing but your peak output voltages, because this is the voltage you are feeding to the filter. So your V peak out is nothing but the rectified voltage. So if you want to do those modifications on your formula sheet, you can do that too. So another important thing is, before start using it, this frequency. For half wave, you just keep the signal frequency, whatever the frequency given it to you. But if it is a full wave, that F should be double, because this stage is coming after the rectifier stages. Rectifier will automatically makes the frequency double. Yes, you still multiply by 2. This 2 is not already being multiplied. This 2 is just in the formula. This F is already going to be 2 times F if it is a full wave. If it is a full wave. So be careful that frequency should be, wherever you see frequency, if it is a full wave, you double the frequency. That 2 right here is not doubling. It's already there in the formula. You should double the frequency when you are using a full wave rectifier. That's the only couple of things I want to point out. After that, it's pretty much how to use, just putting in the formula. For the ripple factor, of course, if you multiply it by 100, what you will get is the percentage. Right? So if you ever ask for percentage, all you do is multiply it by 100. So these are pretty much, as I implied before, because when the signal passes through filter, it will becomes, once you charge, you kind of discharge like that. So this is still kind of fluctuating signal, correct? Right on the top. So this one is your peak to peak ripple. Whatever that peak to peak you have right here. But from here onwards, from the bottom all the way to the reference, that's your, whatever the original DC value is, you are going to get.